Hi, this is William from the University of Chicago Reproducibility Journal Club, and this video is an overview on the topic The Myth of Self-Correction, where we discuss the paper The Natural Selection of Bad Science, written by Smaldino and McElreath in 2016. So, regarding the principle of self-correction, so let's start off with the broad context. In 2005, John Ioannidis wrote a very notorious, controversial paper where he suggested that most published research findings are potentially false. Now, a potential pushback against that sort of argument is that science works by on the principle of self-correction, that false findings will eventually be phased out by non-replications or by better studies that show what the correct lay of the world is. However, James Hedders here, error detection scientist and host of the Everything Hurts podcast, makes a very great tweet here where he says, "Science is self-correcting, sure, when we correct it, not because of magical progress." So the point here is that scientists need to do the work to correct science. And this paper, while we might have this feeling that this is happening in science in general, the Smaldino and McElreath paper takes the next step by doing some modeling and a meta-analysis, and that's what I'm going to overview now. So in the natural selection of bad science, the name of the title is intentional. So the natural selection is meant to invoke the idea from evolution, where the traits that help you survive are selected for and then get transferred later into the next generations. So here, the thesis for the paper is that bad scientific practices / habits are naturally selected by the current incentives. So a quote from the paragraph from the paper: "The incentives of contemporary science encourage, reward, and propagate poor research methods and abuse of statistical procedures." So let's talk a little bit about what the current incentives actually are in science. Well, if to go further in science, to keep getting hired, as for example from a PhD to a postdoc to academic positions, it requires a publication record. So the average number of publications at time of hiring is increasing. It's 22 in 2013 compared to just 12.5 in 2005 for evolutionary biologists. And I think this sort of comparison is valid across all fields of science. And another thing is that there are more PhDs than there are permanent academic positions. So because there is competition for those permanent academic positions, the selection process tends to lean towards those that are from an elite university with very high publication rates. So having a prolific publication record is a large incentive to continuing on in science. So this tweet from the Real Scientist account, note that this is not by Daniela because it's a rotating user account. You can see here, for researchers, excellence is based on the number of publications, especially high impact factor ones, and the amount of grant money you've brought in. And the grant money point is very interesting because what kind of research is funded is typically not the most rigorous research. It's probably the most shiniest research, or goes to the researchers who have the best publication records. And we'll discuss this in a bit through the paper. So journals are more likely to publish positive results, whatever their truth value. Researchers who obtain more positive results, so more significant results and publications, whatever their truth value, are more likely to be hired. So the logic is that if we employ the scientists that employ the techniques, purposefully or not, that drive up the rate of false positives and that drive up the rate of their publications, will continue on, will survive, hence the natural selection. And Richard Horton, editor-in-chief of The Lancet, the prime medical journal, says that part of the problem is that no one is incentivized to be right. So there's the incentives do not link to the truth value, they just link to finding positive results. So in Smaldino and McElreath take this approach to answering or evidencing what is happening with science. So they show that firstly that statistical power has not improved in the past 60 years. As Ioannidis in his 2005 paper suggested that a high false positive rate is due to a lack of statistical power in our findings. And you can see here in this graph, what Smaldino and McElreath did was they took all the papers that had previously done some sort of statistical power analysis in their literature and just did a meta-analysis of those. And you can see here, they've plotted each point. There is no increase in the best fitting line. So the R squared value was something close to 0, had like 4 zeros before a number, so 0.00002 or something like that. So it's very low, so there's no increasing trend. And furthermore, if you look at what the mean statistical power is, it's around 0.24, and that's very low. Just for context, the recommended statistical power value that gets thrown around is around 0.8. So if there is a true finding, you have an 80% chance of finding it. Here, it seems to indicate that our power is at 24%. And as Smaldino and McElreath outlined in their paper, this may be an overestimate because journals tend to publish positive results. So those negative results are put into a file drawer and don't see the light of day, and so on and so forth. So this is a very stark overview of what has happened in science for the past 60 years. There's been no improvement in statistical power. So beyond that, Smaldino and McElreath do some modeling, some interesting modeling about how science might change over time. So this is how they do it. Labs are given a characteristic power and effort. So power here is akin to statistical power. It's the ability to identify a true association. And effort here is a nice little wrinkle to what's happening. It's the time taken to perform the research, and you might link this to statistical rigor. And this is a nice parameter to have because typically the most rigorous research will have more subjects to improve the statistical power, will have more replications, so they'll repeat the experiment to ensure that the effect they're looking at is reliable, rather than someone who just goes to the lowest possible number of subjects and just essentially p-hacks their way to a positive result or significant finding. And so I think in their model they have 100 labs. I won't go into the maths here, but you can see here from the simulation, the alpha rate or the false discovery rate here plotted on the y-axis on the left. You can see as time goes on, so as with each iteration, this rate increases over time and eventually plateaus at a very high false discovery rate and a very high alpha rate. And on the other side, on the flip side, so on the y-axis on the right-hand side, you can see that effort goes down. So as time goes on, the labs that have low effort are selected for. So the labs that take the time to perform rigorous research eventually aren't selected for and are gone. And that as a result, the false discovery rate increases. And that's problematic for science. Another wrinkle to this is the authors Smaldino and McElreath, they add another parameter, which is replication. And so note that in science, replications tend not to be published because they're not as shiny as a new positive significant finding or a new positive effect. But here, the idea is that replications might undo those false positives, those false discoveries. So here, this lab is the replication parameter is varied amongst these labs, and it's allowed to evolve. We'll see whether over time replication is selected for. And you can see from this figure, the same kind of effect occurs. So as before, the false discovery rate and the alpha rate go up, they trend up and plateau. The effort is drops down to 0, so it's not selected for. And replication as a parameter, so are the labs that replicate a lot selected for? Not really. You can see over time, it might increase a little, but doesn't increase nearly enough to offset or undo this false discovery rate or this alpha rate. And why is that? Well, one possibility is that the labs that have high power and low effort will pump out all these publications, and they will contribute mostly to this false discovery rate. And what might happen, let's connect this to the context of real life science. So the labs who have high power but low effort, they're going to have the high publication rates. And then the grad students from that lab are the most likely to be hired as postdocs and then later on start up their own labs. And those research practices or those methods that bring out a high power, so maybe a high false discovery rate as well, will then remain in science and grow on. And hence, as time goes on, you might see this increase of the false discovery rate and alpha as is shown in the model. So yes, so to summarize, why is replication ineffective here? So it's a key point here because replication is not often shown to be ineffective. Most people say replication is great. And the point here is that replication is useful, it's helpful, and we need replications. However, the current model of science, or the current incentive models of science, or the structure of science, is not selecting for replication because some low effort labs escape being caught producing false positives. These labs get the funding and graduate student success, which then select for lower effort and increased numbers of false discoveries. So in summary, rewarding publication quantity selects for methods that produce the greatest number of publishable results, and that means the poor methods that produce high false discovery rates with low effort. Replication is ineffective at stopping the evolution of bad science. That it's not selected for to offset that increase in the false discovery rate. And what that means is institutional change is required to shape the kind of science that gets done. So whether it's intentional or not, we need the incentives in place that is linked to our truth of our findings, not the fact that we produce a significant result or not. So in presenting this paper to the University of Chicago Journal Club, I want to highlight 2 points that came out that were really interesting. The first one is that our experience of selection committees suggests that some are now considering open science and research methods. It might be listed in their job requirements. However, it doesn't seem to be backed up by what is actually happening. So there's sort of two forces that we've observed. One is that because of this kind of movement, those researchers who have a really prolific publication record are sort of questioned. Their selection committees are sort of wise to the fact that they may be gaming the system, and so they'll be a little bit more critical now about those kind of publication records. However, those that are considering those open science and research methods, they're still biased by these publication numbers and impact factors. So one of our journal club, suggested that it was only considered until they raised this question. So often in the discussion or in the job talk, the committee will just go on about their papers or their published papers, but not really mention anything about their open science or their research practices. And even before getting to that job talk stage in that selection criteria, those decisions will often be biased by your publication record and the impact factor of your publications. So those that with high rigor, who have lower publication numbers and probably lower impact factors if they're doing a lot of replications, will not be selected to give the job talk interview in the first place to sell themselves. So there's still that bias going around, even though selection committees might commit to saying that they're looking for someone with open science or research methods practices. And an interesting solution that was raised by one of us in the journal club was that maybe we should be educating undergraduates more, so including this kind of reproducibility, statistical analysis, research methodsy kind of content in the undergraduate course, so that when they elect to join labs in graduate school, hopefully they'll be incentivized by selecting those that have obvious open science research methods rather than those that have the shiniest, most prolific publication record. And this might help undercut this incentive structure, because we know that labs are most productive when you have many graduate students, and we know that a lot of research is the sort of horsepower, the work is done by graduate students. So that's an interesting solution, and yeah, hopefully it's clear that incentive structure needs to change at some point. So that was our discussion. Hope you liked my overview, and hope you enjoyed this video.